Okay, so thank you very much. So I would like to thank organizers for inviting me here and to give me this opportunity to say some, express my gratitude to Bernard for his so thank you, Bernard, for being inspiration for such many generations in mathematics, and happy celebration. Okay. Today I would like to introduce some special kind of partition of unity, which is, I think, can be interesting for those who are working in semi-algebraic geometry. So this talk is based on my paper with common paper with Wieslaw Pawlucki and Beata Kocel-Cynk. It was published last year in Mathématiques. Okay. So let me start by the beginning of the story. So at the beginning was actually the Calder-Zygmund theorem, which comes from PDEs. So let me state the theorem which was our inspiration. So you have a closed subset, and it appears that then, so I will just, let's see, so then there exists a C infinity function F. Maybe here on the complement of W in range of positive values, such that it is equivalent to the distance function. Okay, so such that there exists a positive, and such that we have okay, so this is the distance function to the W. Okay. And secondly, for any multi-index, there exist some constants such that you have this inequality. So the all partial derivatives of f are smaller than the distance of the function in the power 1 minus the length of alpha. Okay? So for any order of derivatives, you have this estimate. Sorry. So this theorem is very important in PDEs, especially in elliptic equations, and you can just work around the singularity, actually, in this small open set around the singularity. So this is very nice, but it's nothing to do with the singularity. Okay, so we started to wonder if we can give a semi-algebraic version of this theorem. Okay, so what will be instead? We suppose that W is semi-algebraic. Okay, so this, and we want to have something like this. So the theorem will be stated that actually we have Nash function. So there exists a Nash function. Okay. So we have C infinity with semi-algebraic, and then we want this one, but there is something that we can't have. So we can't have actually this estimate for any derivative. But what we can have, that for any p, so if we fix p, so we fix any positive integer. Okay? So then we can find such a Nash function that this will be hold for any alpha of length not greater than p. Okay? And so it is possible to prove it. So this is our semi-algebraic version of this theorem. And so usually when you want to do something, to obtain something like this, it's good to do it locally and then to glue together the small parts of this estimates. Okay, so you do locally, and then by means of some partition of unity, you glue it. So actually, this so my object of this talk is to introduce this special partition of unity, which allows us to prove this theorem. Okay, so let me now define what I mean lambda p partition of unity. So from now I will fix W in an semi-algebraic closed set. Okay, and actually you can work in any minimal polynomial bounded structure. Okay, so it can be definable in a minimal structure. Okay, so I will say at the end, I will say some difference. Okay, so we fix a closed semi-algebraic subset, and we call a function f, which is defined on the complement of W. It's not necessary in CP. We say that such a function is maybe p is again some positive integer, and k is some integer. Okay. So we say that f is lambda pk w regular if we have this something like this. So if all partial derivatives up to the order p are smaller than distance function to wk. Okay, so alpha here is like this. Okay, so actually, so we would like to find some lambda p1 regular function. Okay, in this theorem. And this notion actually is, if you know the works of Krzysztof Kurdyka and Wieslaw Pawlucki on Whitney extension theorem, they introduce lambda p regular functions. So actually k is 1 and w is actually the border of omega where the function is defined. Okay, so I will say something more. So now I can state the theorem. Yeah, so maybe I will write here on this table some more general theorem of this Calder on Zygmund. So for W, closed semi-algebraic, and take now any function, so say G on Rn R, semi-algebraic Lipschitz, such that G is vanishing on W. Okay, so G on W is 0. Okay, so then there exists a Nash function. Sorry, maybe, no, sorry. Lambda P1 W regular function F such that for any kappa greater than 0, we can approximate actually G by F. Okay, so we have such a such approximation of G by F for any. Okay, so we have. So if you look at this theorem, so actually it's using this theorem and Schiotta-Efronson approximation theorem, we can obtain this one. Okay, so because firstly we obtain such approximation of, so by G we take our distance function. Distance function on semi-algebraic closed set is of course semi-algebraic and Lipschitz. So and is vanishing on W. So we can approximate it like this, and then having this F, we can approximate it by Nash functions, which is the Efronson-Schiotta theorem, and then because the Nash functions are dense in the CP topology. Okay, so we can approximate it by this function by P, and then we have our theorem. So mostly it is important to obtain this one. And so yes, so for this so usually when you want to approximate the function, you need some partition of unity. So maybe I will, maybe I give you what I mean by this partition of unity. Okay, so it's very special. So it is not like I'm sorry, I'm too fast. Yes, because okay. So if you take any set in the complement of W, which we fixed, okay? So we define this. Z can be arbitrary set. So we define the neighborhood of this set. So we fix some eta positive, and we define the neighborhood of zeta. So this G eta of Z with respect to V, like, so we take all points in the complement of W such that okay, so this is something that if you have this W, you have your set here, so we will have some neighborhood of special kind, okay? And so our partition of unity is this. So we take, this is a finite partition of unity. So we take finite semi-algebraic sets which are covering the complement of W, and for any eta positive, and for if we fix P the positive integer, then we can find lambda P0 W regular functions phi I. Such that the support of phi I is contained in the G eta U I W. By support of phi I mean the closure of the support in the complement. Okay, so this is sub of phi I is the but in the complement. Okay, and such that they sum up to the one. Okay, so phi 1. Okay, R1. Okay, so in semi-algebraic case, it's natural that we have finite covariant ring, and then why I write in the title that this is somehow Whitney semi-algebraic partition of unity because of this function phi I lambda P0 regular. So if you look at the partition of Whitney, so they wrote this equality. Okay, so the function which will constitute the partition of unity has this inequality. Okay, so it's like some. Okay, so it is. So we'd like to prove that we can do it. Okay, and I can't present the proof of this. It is very technical, but I will give you a flavor of what we use. Okay, so there are two ingredients actually. The first one is the Lipschitz lambda P regular stratifications. Okay, so let me say what I mean by this. So let me start by what I mean by lambda P regular serre. So as I told you, there was actually this notion was introduced by Krzysztof Kurdyka and Pawlucki. So this is natural definition by induction. So maybe yes. I start by the definition of open lambda P regular serre. Okay. So in Rn. So when n is equal to 1, there is just an open interval. Okay, so open interval, and in higher dimension we have we do it inductively. So will be so this cell will be of such a form. So this maybe that. Okay, I will just write some. Okay, and phi I, so phi 1 and 2 is going from some cell. So this is in, okay, this open lambda p regular cell. And there are lambda p1 regular functions, or can be minus or plus infinity. Okay? So this is the inductive definition of a cell. And in general, if you want to have lambda p regular cell of dimension n in Rn, so it will be of the form, this is the graph of a function, so sorry, so I should write this here, okay, because it doesn't make sense if I okay, and T is some open lambda p regulars, and phi is lambda p1 function. Okay, so this is natural. Yes? Yes, sorry, yes, it's better to have open, so thank you. Okay. And what is nice with this, that it can be shown that if you have any finite family of semi-algebraic sets in Rn and some function, semi-algebraic, then you can find the stratifications, so that the strata are lambda p regular cells, and which is adapted to your sets. Okay, so it's compatible with your sets. So maybe I will write here. So this is so take a semi-algebraic, it's A1 AK semi-algebraic sets, and G there exist stratification of Rn compatible AIs and G, but lambda p regular strata. Okay, so the strata are lambda p regular cells, but of course these cells will be depend on the coordinate system. So you have to choose the coordinate system to set. Actually, you can just take from the axis. So you can just take the canonical. You don't need just it's enough to take the axis of coordinate system. Okay, but of course each cell can be in different coordinate system. Okay, so this is very powerful statement, and then very nice. And actually, they use it to prove the Whitney extension theorem in semi-algebraic or more general or minimal case. Okay, so using these stratifications. And actually, we'll also use this to produce our partition of unity. So this is one of the ingredients, and the second one is the maybe here. Maybe here. This is possible. So let me say some very easy observation of these functions lambda k regular. Okay, so first one is that if you have two, so f and g, maybe, so fix k, l and p integers, p positive, and take two functions. So f be lambda pk regular with respect to w. W is always fixed, and g lambda p l w regular. And we suppose that because in our definition of lambda p regular functions, we have just only this just for the derivatives. So would like also assume that f x smaller than a distance of w and yeah, but okay, for some constant a. Okay, so then you can suppose that if you take the product of this function, you obtain what we can obtain? What kind of function? So if you take a product of such a functions, you obtain a lambda p k plus l regular function. Just computation is not very difficult. Okay, so this is the first observation. The second one is then if you take, so we fix still k and p. So if f is lambda p k regular, and moreover we have this estimate. So okay. Of course, a here are some positive. It's not interesting. if you take, so then 1 over f is lambda minus k w regular. Okay? And the third one, which is, so if you take any, so if f is lambda 0 regular, and you take any function which is Cp, then phi composed with f is still lambda p0 regular. Okay? So these properties are really easy to see. That's make a calculation. It's not, but they are very useful in our yeah. Okay. So maybe I will just erase this. So usually when you want to obtain some partition of unity, you in classical way you use some Urison lemma. Okay, so let me say how we obtain this. So we have definition. Okay. So if you take any so take Z any subset of complement of W, and we say that the property Bn Z. Okay, so this property is that there exists a function so for any, take any eta positive, a lambda p0 w regular function psi in R. Okay, such that psi in the restriction of the small neighborhood of, so you try, I hope, yes, so you have this G eta, so G rho of ZW is equal to 1 for some rho smaller than eta. Yes. And the support of psi is contained in G eta ZW. Okay, so it means that if you have this your W here with zeta, so you can, on the small neighborhood of W of zeta, our function is 1, and on the larger it is the support is contained in this larger neighborhood. Okay, so outside it is 0. And yes, I think this is the most technical part of the proof. So to show that actually this property holds for all semi-algebraic sets. Okay, so term is that for any zeta semi-algebraic property V and zeta W holds. Okay. And once we get this, it is very easy to define the partition of unity, because if we take the U1, so we take, so we construct, we have our functions. These functions are lambda p0 regular on some neighborhood of U, and then our phi will be, phi will be maybe like I write psi. Okay, so psi will be here. I will need phi I. Okay, where phi I are psi here. Okay, for U I. Okay, it's clear. So this is really technical, and actually we do it by induction on the dimension of zeta. Okay, so it is easy to have when there is a point. It is easy, but what is important is to observe that if you have property B and zeta 1 holds for some zeta 1 zeta k, then this property Bn holds for the sum of zeta 1. Okay, so this is crucial to see. So this observation allows us to proceed by induction, actually, because we can then stratify our set and then show this. But there are some technical problems, and then you have to find many calculations. So this is not easy to proceed this induction. Some two pages of calculation. Okay, so once we obtain this, we can have our partition of unity, and then once again to show this theorem, we need to stratify with this lambda p regular strata, and then we for each strata we can construct such a function which is good approximation, and then we glue by partition of unity. Okay, so this is the main idea. And so till now, actually we can work with any minimal structure. Okay, but if you want to obtain the Calder-Zygmund theorem in minimal, it is a delicate problem, because actually what we do, so having this, so starting with distance function, yes, so we have this, so how we proceed with, so we have our approximation, which is lambda p 1 regular, so it is of class CP, but we want to so now we need Nash function. Okay, so we have to approximate it by some Nash function with also with containing the derivatives. And we can do it in semi-algebraic case. This is the classical Efrenson-Shota theorem. But in a minimal case, actually we proved recently with Guillaume that we can do it, but no, so we can show that the Nash functions are dense in the C1 topology, but not in, so we didn't write for P for any P. Okay, Actually, it is true, I think, because we have some handwritings and it is okay, but it's not published, so I can't swear that it is really true. But it is very technical. So passing from 1 to p to arbitrary p is very technical, but the idea is, I think, is clear. So should be okay. Okay, so for some algebraic case you can do it, and actually you can always do if you have this Nash approximation theorem. So in some special or minimal structure, there is known that it is true. Okay. Yeah. Okay. So this, and so I have some small time. So maybe I will. So there is. Why it is interesting, this theorem? Okay, so from this it is very, you have for free actually that if you have a function. So this is a very natural question which was solved years ago, but so if you take any semi-algebraic set, is it the zero set of some CP function? Okay, and it is true. Of course, it was showed by Pawlucki and Birston years ago, maybe 20 years ago or more. I think so. But we can have this from free because if we take distance function. So we have this regularization of distance function, and this regularization of distance function, if you take the p power of this regularization, will be this our CP function, which is zero set R W. Okay, so this for free. And the second one, which is also for free, so that if you take any compact semi-algebraic hypersurface, you can approximate it by smooth ones. Okay, so what I wanted to say. So maybe I will write this. So if you have no compact nowhere dense semi-algebraic set in Rn, so there is a family of Nash compact hypersurfaces. Take HT such that the limit in the Hausdorff distance of HT to W. So the HT are converging in the Hausdorff distance to the W, such that yes, okay. So you can approximate any compact Nauer dense by Nash compact hypersurface in the Hausdorff distance. Okay, and this is like you take just by HT, you take the preimage of our regularization to the distance function. And of course, this function has only finite number of critical points. So then, starting from some point, then you have Nash function, HTR as Nash. Okay, so and then this, of course, you have this approximation. And if you want to have some more, so if you want to control the dimension of this, so we can actually do something more, control, so taking any semi-algebraic set with k-dimensional, we can also approximate by same dimensional Nash sets, but it is a little bit more complicated. And just to finish, so, but it is not written. So I think that we can, using this partition of unity, we can obtain another proof of extension, of Whitney extension theorem, which would be a little bit simpler than the original proof of Christoph and Wieslaw. Okay, so thank you very much.
Thank you for this talk and for finishing all in time. So there is time for a few questions. Is that the microphone? Organized? Is that the one mic? I just mandatory. Oh, okay. Just speak loud enough. Questions? Christoph.
Semialgebraic case, you obtain f Nash function.
Yes.
But first you construct a semialgebraic function which satisfy these estimates.
Yes.
And then you find the approximation
yes.
of this. And what is the main argument for this approximation?
No, so you can construct, the main argument is that you can use a, for instance, Sciota approximation theorem, yeah. Okay? Because you can approximate with control of derivatives.
Yes.
Okay? So if you have some CP function, you can approximate it by Nash function.
Yes, okay. So, because this, of course, makes sense in semi-algebraic category. No, for O minimal does not make sense.
Why not?
But because what is Nash function in a minimal category?
Yeah, it's not Nash, but it will be C infinity.
Oh, yeah.
And definable in this structure.
Yeah. Okay. So I want to say something nice for me. I believe that, that this lambda p regular function, perhaps they can somehow replace this reparameterization lemma of Gromov and Yomdin, because in fact in the proof we use some ideas of Gromov to in the proof of this this first paper and this and probably. Well, in some application, you may replace it by this reparameterization theorem, which is highly non-trivial, by this a bit simpler stuff.
Okay, maybe one last question. If there is any. If not, let's thank the speaker again.